Alright, I'm very sorry about that. I understand why my tablet doesn't work sometimes. It's just, I'll test it, and I'm like, oh, it works, and then we'll go to use it, and then it doesn't work. So... Alright, so you can see this on the previous video. I'll include that in the playlist, the 7-minute version of Polarity. But what our plan is for determining the polarity of a molecule is that we're going to look at the Lewis structure, draw it as accurately as possible again. We're going to write out polarity arrows using arrow notation. Don't use deltas here. We're going to use arrows. And then finally, we're going to look at where all the electrons get shuffled around to based on where these arrows go. So, like I said before I was rudely interrupted by my technology, we can calculate the difference in electronegativity by looking up... Oops, sorry. C is 2.5. By looking up these numbers. And then we're going to assign a vector based on the number. So the number actually represents the magnitude of the vector that we're drawing. And the direction is going to be indicated by the geometry. Now, I'm using those terms for people who have taken a physics class before and know what a magnitude and a direction are for vectors. For our purposes, we're not going to care so much about the magnitude, but if you're just curious about how polar something is, or if there's a polarity gradient, then yes, we can use the magnitude of the difference in electronegativity as our guide. So I have two polarity arrows. One points from the carbon to the oxygen on the right. One points from the carbon to the oxygen on the left. Since they both have the same difference in electronegativity, they should have the same magnitude. Now, if I add two arrows, or two vectors like this, we add them head to tail. So wherever the first one ends is where the second one begins. And we just keep doing that over and over and over and over until we run out of vectors. And so you get something that looks like this. So there's my first vector. I started over there, and I ended somewhere to the left of where I started. We're going to start the second vector by putting its tail end at the head of the first arrow. So we'll do that. And you'll notice that you just kind of end right back where you started, because you go to the left, and then the other vector pulls it right back. This is how you add arrows together in vector notation. Now, because we ended where we started, there is no net polarity. So CO2 is considered to be nonpolar. Any molecule that is completely symmetrical in all possible orientations will be nonpolar. So if you have like a linear molecule and all two things are the same entity, so they're both oxygen, they're both fluorine, whatever, nonpolar. If you have something tetrahedral and all four things are the same entity, nonpolar. Now, water is bent, and it is symmetrical, but it's not perfectly symmetrical. So you could rotate it along one axis and get the same result, but you can't rotate it along the other axis. So it is not perfectly symmetrical. And that's where you get the interesting stuff. So we're going to look at that here. So we've got SO3, which is trigonal planar, and we got water. Now, for simplicity's sake, I'm just drawing these as arrows with a magnitude that is approximately that of their electronegativity, which, again, not super relevant if all of the bonds are the same. So here's the first one. So I started there, and I made this all one animation because that was just how I made it work. These are really hard to animate, it turns out. Mostly because you can't see the endpoint when you're setting the animation. You just have to play it over and over and over. So you'll notice that for this SO3 molecule, I ended up back where I started. So SO3 must be nonpolar as well. But what about for water? Here goes water. Oh, look at that. We did not end where we started. In fact, if I was going to sum these two together, I would say, oh, well, if I started here and I ended here, this is my overall result, right? So that's what I get. So I can take that and I can just plop it right over the structure itself, and that's the overall polarity of the molecule. So water is polar, and based on how we have drawn it, the positive side of the molecule must be the side with the hydrogen sticking out, and the negative side must be the side with the oxygen in the center. And that checks out because oxygen is way more electronegative, right? It's going to pull the electrons towards itself. So it makes sense that overall, for the molecule, it would behave as if it was just one bond with the electron shifted towards oxygen. So this is how polarity is determined. Now, obviously, you don't have arrows sliding around on paper in front of you. You have to actually draw these and then try and transcribe them manually. And that could be very tedious. So if you are trying to draw a Lewis structure and transcribe the polarity by drawing arrows and then moving them over with your fingers, the examples that we're going to use are going to be pretty obvious. Like, oh, there's obviously nothing pointing back at that. So you could see down here in the water example, there's no arrow pointing down. So there's no way I could ever get back to the start, right? There's just too many things that are pointing up. In the top example, everything's pointing radially outward. And all the angles are equal. For the most part, as far as they're concerned. Because of that, we get a result that is very, 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 very close to being at the origin. So we would say nonpolar. So as long as you get close to the origin, nonpolar. I've tried to do this with a tetrahedron, and it's not as convincing. But here's my attempt to do this illustration for CH4. I tried, I really did. Like, it's not bad, right? It's hard to do 3D and 2D. But you can see that I relatively ended up close to the start. So, nonpolar for that one. But for ammonia, everything again starts to point kind of in the upward direction. And so when I draw all these, you'll notice that that's kind of where I end up, right? So my molecule for ammonia is polar, with the positive side being the collection of H's at the bottom of the pyramid, and the negative side being the nitrogen at the top of my trigonal pyramid. So again, try to do the best that you can. For the examples that we're going to stick to in this class, you're going to find that the answers are pretty obvious if you've drawn the structure correctly. That's really the sticking point here, is you got to draw the structure as correctly as you can based on your Lewis structure, or the molecular geometry. All right, so you've seen my examples. So what I want you to do is I want you to try and draw these molecules as close to the correct geometry as you can, and tell me if the overall molecule is polar or nonpolar. And if it's polar, indicate a direction. Up, down, left, right on your paper, or whatever. Obviously, your drawing is going to be different than mine. So for your polarity reference, say relative, it points towards the, and then indicate an atom. So in this first one, maybe it points towards the P. You will need to go look up the electronegativity table or just predict trends based on position. For instance, P is less electronegative than Cl because it's further to the left. That's good enough for our purposes. I'll give you 5 minutes to do this, and then we'll go over all the answers, and we'll keep going. 2 more minutes and we'll go over the answers here. All right, let's go over a few of these. If this pops up here, there we go. All right, so I'm going to draw the Lewis structure fairly quickly here. Since the learning objective here isn't to draw Lewis structures, it is to figure out polarity. So the geometry that you should have gotten for PCl3 is trigonal pyramidal. And this is a molecular geometry, by the way. So now I can draw my polarity vectors. So chlorine is more electronegative than phosphorus. So I'm going to draw my arrows. Oh, that color's too light. Hold on. There we go. Away from the phosphorus and towards the chlorine. And you could see that the overall is going to be pointing in this direction. So we would say that this molecule is polar. And to be more specific, we could say it's towards the Cl side. Now, if I had to draw this in 3D, this is what I would do. So there's my three-dimensional molecule, where I would have Cl, 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 P. And the polarity would point from the P through the base of the pyramid. Actually, let's do it this way. Like that. I tried to draw it right in the center, but I also kind of drew the top of the pyramid a little skew there. So it points from the top of the pyramid through the center of the base, I guess we could call it. Now, that might be a little more detail than you need to know, but just in case you wanted a more three-dimensional perspective on it. CS2 is linear. Also, if you go and look up the electronegativity difference between carbon and sulfur, you get virtually zero. Even if I did draw arrows like this, which I don't even know if this is the right direction to draw them because they're both 2.5, your overall result would still be nothing. So CS2 should be nonpolar. For C2Cl2, you should get something that looks like this. A C with a triple bond to another C, and then each chlorine on the sides looks like that. Now, a carbon-carbon bond, those are the same atoms, so there's no net polarity for that. But there is a net polarity for these. Chlorine is more electronegative than carbon. And when I add those together, well, because the whole thing is linear, so each of these angles is 180 degrees, I get no result for my polarity. Next, we got SCl4. And I believe SCl4 is a seesaw. Let me count real quick. 28, 34, 8, 16, 24. Yeah, okay. So this is what SCl2 or SCl4 looks like. And so I can draw my polarity arrows. Chlorine is more electronegative than sulfur. Like that. Now, if we look at our geometry, and I'm going to draw a little sketch of my geometry here. So I've got up and down. And then on a circle going around the origin, I have one going forward, one going backward, and then one coming out to the side here, right? So this is my trigonal bipyramidal. This one, however, is just an electron pair, so we're going to ignore it. So that's how our geometry comes about. Which means that any polarity arrows going in these directions must completely cancel each other out, right? So these two neutralize each other because they're pointing in opposite directions. And if all three of the trigonal planar in the middle here they would cancel out too, but they aren't doing that. They instead point in this overall direction. So overall, this is the result that you get away from the electron pair on SCl4. And so SCl4 is polar. That's why you got to be really careful with drawing the geometry. We're going to see that again here for IF5 because IF5 is square pyramidal. And so it totally matters which direction you draw it. So there's my IF5, and then I got to put these down here too. And so here's my 3D sketch of that thing that I've drawn. So my I is right here in the middle, and then I've got F, 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 F. So you can see the square pyramid there. So when I draw all these bonds, fluorine is the more electronegative one because fluorine beats everything, right? And I got one point like that. So you could see that me doing these two, those cancel. And me doing those two, those cancel as well because they're just opposite from each other, right? The only one that survives is this one. And so overall, IF5 is polar away from the electron pair and towards the fluorine opposite to it. Now, it's not a great analogy to say, oh, I'm always going to point towards or away from an electron pair on the central atom, because you might end up going between them. But if you see electron pairs on the central atom, a lot of the time it's going to be polar, but not all of the time. For instance, if you get a linear arrangement of atoms from a trigonal bipyramidal, so 5 electron groups, 2 or 3 of which are electron pairs, you still get something that is nonpolar because it's completely linear. So avoid trying to make a generalization with, oh, there are electrons on the central atom, it must be polar, because there are instances where that doesn't work. That said, almost all of the time it does work. So that'll at least tell you, oh, it's probably polar. Let's investigate this a little bit more. Okay? That's polarity. And again, your job is to draw the molecule to the best of your geometric ability and then indicate the polarity over it by constructing a sum from individual bond polarities. All right. Now, that would normally be the end of Chapter 4, and we could go start Chapter 5, on the last day of lecture. But for whatever reason, we are asked, we being chemistry faculty, to include section 10.1 in the text, which is a brief discussion of intermolecular forces. You will see this again in 162. However, if you're taking like cell bio or something like that, it's very, very, very important to have a basic understanding of intermolecular forces. So when we come back from the break here, we're going to go over the different intermolecular forces. And then I'm going to talk about the pitch drop experiment, and I'm just going to link you the video, and we're not going to do anything with that, probably because we'll be out of time. And then we'll talk about how we're going to get through Chapter 5 at the end here. So let me put this on the screen here, get the timer up. And I'll see you in 10 minutes. So take a break. Oops, hold on. Do you want to update? Never. All right, we'll see you in 10 minutes. Whoops, I hit something on accident. There we go. Let's wind that down. Alright, so let's talk about this last bit. So this is considered to be part of Chapter 4 for our intents and purposes. So when you take the Chapter 4 quiz, there will be questions on intermolecular forces on there. So let's get started on these. So the premise of this section is to talk about how molecules hold together. So we've talked a lot about bonds. So if this is my water molecule, and these are my bonds that hold atoms together, are there interactions that hold molecules together? And the answer is there absolutely are, because otherwise all molecular matter would just repel from each other, because they will bonk into other particles and their electrons will repel each other. But there must be certain arrangements that allow molecules to attract to each other, because that's how we get solids, for instance. Or how molecules stay a liquid at room temperature when others are a gas. We're going to talk about these forces in great detail in this section. So, the force that holds molecules together into whatever phase it is that we observe are called intermolecular forces. And so we're going to discuss different approaches for molecules to attract to each other. However, all of them follow the same premise. They are all based on charge. And so they all follow Coulomb's law. So they're all just electrostatics in action. If a molecule makes a positive component, it will be attracted to another molecule that makes a negative component, no matter how weak the components are. The magnitude of the component made will govern the strength of the attraction. Now, on the far right, you can see that I have made a column that says intermolecular forces. For a gas, all of the molecules in a gas have a weak attraction to each other. This is because gas particles have very high velocity, they're moving all over the place, and they don't really see each other. Whereas molecules in a liquid are brushed up against each other and relatively close. The analogy that I could think of is like going to a bar to meet people versus going to a highway and trying to meet people as they drive past you. One of those is the liquid, the other is the gas, right? Like, it's virtually impossible for you to communicate with somebody standing on the side of a highway as cars go streaming by you. They're just moving too fast relative to you. Even if somebody looks at you and is like, hey, look at that cutie, they're going way too fast to stop, right? And they're probably busy for work. But if you're at the bar and somebody sees you, they can approach you and talk to you. And that's entirely by virtue of how close the molecules are. Now, we're sort of going the opposite direction in terms of our explanation here. The molecules are closer because of these forces. And in a solid, the molecules are so close that they're basically locked in place to each other, as if everybody was handcuffed together. So that's where we're going with this discussion. Strong forces hold molecules closer together, and the strongest forces lock molecules into a rigid structure. So again, solids have forces that hold them into a structure. Liquids have a weaker force. It still holds them into a relatively tight distance, but they have freedom of motion. And gases have very few interactions between particles because they just have so much kinetic energy. Plasma is basically the same as gas. A plasma is an ionized gas. You do need to heat up a gas hot enough to make it a plasma, so you can think of it as the next step. But we're not going to worry about that too much here. All right, let's start talking about these phases. Hey, guess what? Everybody hold hands with somebody else and leave the classroom. These slides don't work because you're not in the classroom, obviously. So normally what I would do is I would say, okay, what I want everybody to do is stand up and leave. And so everybody goes outside of the room. And that's relatively easy to do because there's like 4 doors in the room. There's 2 doors in the room. What the hell am I saying? Everybody's sitting in various places around the room, and you just all leave, and it takes like 20 seconds. And then I say, okay, everybody come back to your seats, and part 2 of the demo is now everybody hold hands to form one giant linked chain, and now exit. And what inevitably happens is they try to use the same door at the same time, or one end of the chain goes out one door and the other end of the chain goes out the other door, and then they realize they have to turn around and come back. Yeah, like this is not allowed. We can't do this anymore, right? Like this exercise will get canceled once we go back. I'll be like, okay, social distancing. Everyone's a gas. So obviously, in the part where everybody's holding hands, there are interactions between people, and it restricts your movement. So you can't get up and leave as quickly because your ability to move is constrained by attractions or bonds to other students. Because you're holding hands. You are basically stuck in that position. And then the secret part 3 is, okay, now sit on these chairs where I've put a very high-powered adhesive. And now you're going to be solids. And you'll just remain here for the rest of forever. So, but we don't actually ever do part 3. So on the screen, you can see this sort of in action here. For my solids, I have such strong attractions that I am holding my molecules into this rigid shape. For my liquids, it's a little less defined. And all my molecules are attracted to each other, but only really their nearest neighbor at any given time. For gases, there's essentially no attraction. Now, the reason for this has to do with kinetic energy. As kinetic energy increases, molecules want to move. And if things are moving, it is hard for these forces to take hold. I'm trying to think of what I want to introduce here to keep going. So, as molecules increase in velocity, their temperature actually increases. And we haven't really talked about temperature yet, but temperature is equal to the kinetic energy of molecules. In other words, the hotter it is, the faster the molecules either vibrate or move. If they're in a solid, they will vibrate because they won't leave their solid, but if you heat them enough, then they start to move freely and become a liquid. And if you heat those even further, then they get enough energy to escape the attraction of their neighbors, and then they just take off on their own. Now, the other thing that you can do to force molecules together is instead of adding heat, you can reduce the pressure. We're going to talk about atmospheric pressure and its effects in 162 when we talk about gas laws, but suffice it to say, you can think of pressure as like a giant hand holding down. That's my hand here, so there's the thumb and the fingers. Whatever, right? I'm not an artist. So it's a giant hand holding down the molecules into place. And when you fight against that pressure that is causing our molecules to remain in that state, as you gain enough energy, you can resist that. Now, if you reduce the pressure by putting a substance in vacuum, it tends to change state because there is less energy holding it in place. Now, the opposite process would be if you cool something, you lower its kinetic energy, so the molecules then are closer to each other for longer and start to get attracted, and then start to form a liquid, and then eventually a solid. Increasing the pressure also does that because you just force all of the molecules into a very, very close arrangement. So that's just a discussion on phases here. Let's talk about... We've already talked about pressurizing stuff to make it into a liquid. We're not really concerned about that, though. We're more concerned about where these forces come from in this section. So I've put Coulomb's law on the board, and again, we don't really give a shit about Coulomb's law in terms of a calculation, so we don't care about this constant. We'll change this to a proportional symbol. These are the only terms that we care about. So we care about charge and radius. Interactions that are larger in charge magnitude will be stronger. Also, interactions that are closer are stronger too. So things in the solid state, which are very close together, must have the strongest interactions. Things in the gas state, which are very far apart, must have a very small interaction. Now, because molecules have a much larger distance relative to the bond distance within a molecule, and bonds also follow Coulomb's law, bonds are much stronger than these intermolecular forces. So later on when you talk about bond enthalpy, you'll learn that bonding has a very high energy. It takes tremendous energy to break the bonds in water, for instance. Whereas in order to break the interactions between water molecules, that's not difficult to do at all. You just put the water on the stove and heat it to 100 Celsius, as opposed to breaking apart water into hydrogen and oxygen, which happens at like 2200 Celsius, or something ridiculous like that. So when you boil water, what you are doing is you are separating out the individual molecules from each other so that they are independent. What you are not doing is dissociating all of the hydrogen and oxygen apart so that you have H's and O's streaming out of your pot. That would be very dangerous and reactive if you were making hydrogen and oxygen gas above your stovetop, which contains a heating element, which contains two very volatile gas and explosive gases now. So you've never blown up something by boiling water vapor, thankfully. And that's because you aren't making hydrogen and oxygen. All right, let's talk about these forces. The first force we're going to talk about is the dispersion force. The dispersion force is considered to be a random effect. Random effects are random. What that means is that at any given time, my electrons around the nucleus are in motion in any sort of chaotic pattern that they want to occupy. And so my two electrons can be literally anywhere in this helium atom. Now, in most cases, they are going to be opposite the nucleus from one another. But on occasion, maybe this electron is going about its business and this is the direction it's heading, and this electron is going about its business, and it just happens to be going in the same direction at that moment. And then these two see each other and go, this is where I need the Metal Gear Solid sound. And at that moment, they realize, oh, we're both on the same side of the nucleus. And what ends up happening is that because there are a larger number of electrons on one side than the other, we could write this symbol. This side of the nucleus is mostly electrons. Sorry, this side of the atom, I should say. This side of the atom on this side is mostly just the influence from the nucleus. And so what that means is that if this helium atom had this effect going on, and I had a neighbor next to it, the neighbor might say, oh, look at that positive charge. And its electrons would move in that direction and form this effect, which would then propagate. And this would happen over and over and over again, randomly. Now, the second that this disappears, boop, then this stops happening too. And then it stops on the neighbor, and so on and so forth, right? So this is a sort of like pulsating effect that occurs randomly and provides a very, very, very weak attraction between two entities. This is called the dispersion force. The dispersion force occurs when electrons are unevenly distributed around a nucleus. Now, with helium, this is not very likely to happen because there's only 2 electrons. But when it does happen in helium, you get a temporary dipole. Now, the temporary dipole can induce a charge distribution in any neighbor that is next to it. Does this have to do with Brownian motion? Absolutely, actually. Now that I say that, actually, so Brownian motion is sort of like this. This is more of a quantum effect. However, because the molecules are moving entirely randomly, and Brownian motion is essentially random too, I think they might be related, but I'm not 100% sure now. Anyway, these molecules will attract to each other very, 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 very weakly and only some of the time. Now, how do I make this force better? Well, if I have more electrons, I can make this happen. In fact, the only thing that is needed to make the dispersion force occur is electrons. Therefore, all matter exhibits dispersion forces. So this is the weakest intermolecular force. However, everything exhibits it because everything has electrons, and there is always a random probability that your electrons will be unevenly distributed around the nucleus. Now, in order to make the probability of this increase, we need to have more electrons. So if you have more electrons, you are more easily able to create these dipoles that you see above. And this is called polarizability. Something is polarizable if it has more electrons. Now, counting electrons is tedious, so we just look at something's molar mass. The more molar mass you have, the more electrons you must have as a result. And therefore, the more easily the molecule can be subject to dispersion forces. So for instance, if I looked at helium versus xenon, we would predict xenon has way more electrons. It has 54 of them versus helium's 2. So xenon should be easily polarized and have a much higher attraction to other molecules. Would hydrogen without any electrons also be polarized? By definition, it cannot be polarized in this sense because it doesn't have electrons to polarize. However, it would have a charge. So be kind of careful because polarize means inducing a dipole, whereas something that already has a charge doesn't have a dipole. It has a charge. A dipole is a partial charge. So they mean similar things, but it's very easy to confuse them. Anyway, back to the xenon thing. I actually have on this slide here the boiling point of various noble gases. And you can see that as the molar mass increases, the boiling point increases as well. Now, what must be happening is that the number of electrons in these atoms is increasing as we go down the periodic table here. That's increasing the ability of my molecules to stick to each other. What would boiling be a measure of? Well, if something boils, it has enough energy to escape those interactions, right? So if something has a higher boiling point, it must need more energy to break it free. Therefore, the attractions are stronger. So you can see here that as molar mass increases, boiling point increases too, in the absence of any other possible effects. So the only effects here these substances have are dispersion, because we know that these elements are not bonding to each other. There are no krypton-krypton bonds going on. No xenon-xenon bonds. Now, as you increase the molar mass of your molecule, these forces get really, really, really strong. And so what we're going to do is we're going to make a sort of chart that indicates our intermolecular forces here. So we're going to do this. So on the x-axis, or on the y-axis, we're going to have relative strength. Wow, that's almost better than any handwriting I have ever had in PowerPoint. I'm literally writing sideways. I'm not turning the tablet. On the x-axis here, we're going to have molar mass in grams per mole. And so here's what we're going to do. We're going to write dispersion in blue. So here will be my key. And so dispersion is really shitty at low molar mass. But as the molecule gets bigger and bigger and bigger, dispersion becomes more and more significant and more able to hold molecules together. This is really prominent in things like lipids. So lipids are fatty acid chains of molecules, and they have very, very, very high molecular mass, and they're completely nonpolar. The lipid bilayers that make up your cells are all held together by dispersion, and the only way that we could really hold them together to make a cell, like actually stay a cell and not like disintegrate, is to have a very, very, very high molar mass to have everything attract to each other. All right, so we got dispersion on there. Let's look at some other effects of dispersion. If I have two molecules that have the same molar mass, so these are both C5H12, which means they both weigh about 72 grams per mole. The effect of structure comes into play. Now, on the left, you have N-pentane, and I'm going to draw a little, like, orbit around this molecule. And then I have neopentane, which I'm going to draw like this. And what I'm going to do is I'm going to try and draw a second one of these next to it, like so. There you go. Now, for the neopentane, if there are dispersion forces, the only place that they get to interact is right there, where they touch. For N-pentane, though, I can form all sorts of interactions along the surface area. So if I have a molecule that is much longer and has a larger surface area, that allows me to make temporary dipoles in given spots. So for instance, if I shoved all my electrons towards the center on the top molecule, then the sides would be relatively more positive than the center. that would cause all the electrons to be shoved to the sides on the other molecule, and then I would form this sort of three-part dispersion force. So if I can increase the surface area, I increase the possibility for these locations of attraction to occur due to dispersion. And as a result, we can see that the boiling point of these molecules is significantly affected. This is like a 25-degree difference, 27 or so. You've probably realized by now that we're using boiling point as the rubric of how strongly are my molecules held together, because if it boils at 0 degrees Celsius, not held together very strongly. If it boils at 500, held together extremely strongly. Alright, so I don't really have enough time to give you a chance to go over these examples, so what I'm going to do is, if you're watching this in the future, you can pause the video and try and do these problems. If you're watching this in the present, you could still pause the video, you'll just be behind me. But what we're doing in this case is we're going to select the higher boiling point, which would be the thing that has the stronger dispersion forces. So that's whatever that just has more electrons. So chlorine is a smaller molecule than iodine in terms of its molar mass, so iodine must have more electrons, and iodine would then have the higher boiling point. And you could see that by looking at the periodic table on p-table. You'll notice that all the gases are at the top, and then bromine is a liquid, and then iodine is a solid. Solids must have higher boiling points than gases. Between oxygen and nitrogen, which one has the higher boiling point? Well, oxygen has more electrons, so it's going to have the higher boiling point. Between hexane and octane, octane has more electrons, has a higher molar mass. Down at the bottom here, I have a question for you. Which of these is the gas, which one's the liquid, and which one's the solid? Well, the one that has the highest molar mass must be the solid, right? Because it would have the highest boiling point. And then the one that's the smallest must be the gas at room temperature. And then by process of elimination, this must be the liquid. Now, if you wanted to give a better explanation, you could say, oh, well, why does it have the highest boiling point? It's because it has the strongest dispersion forces. Molecules are held tightly together relative to the other members of this group. And then C2H6 has the smallest mass, it has the fewest electrons, and thus the weakest dispersion forces. And all of this matches up with our little graph that we've drawn so far. All right. Let's talk about other interactions. Any molecule that is polar has a permanent dipole. So our helium atom or our noble gas or whatever had temporary dipoles. So like maybe this is xenon or something. But something like, say, carbon monoxide has a permanent dipole. Right? And as a result, things with permanent dipoles are much, much stronger at attracting to other things than those with temporary dipoles. So on the bottom here, I've shown you acetone. Acetone has a nonpolar part and a nonpolar part that we don't care about. But the carbon-oxygen bond right here is very, very polar. And as a result, we make a delta plus and a delta minus that are permanent. These don't go away based on the random motions of electrons. And as a result, acetone exhibits a dipole-dipole force all of the time. So a dipole-dipole force is much stronger in magnitude and occurs because a dipole exists on the molecule. Now, what this means is that if I take two of them, I could just align them like this. They would attract to the opposite charge of the other thing. Now, this interaction between dipoles causes a large jump in boiling point between molecules that don't have it. So, for instance, butane, which is just carbons and hydrogens, has only dispersion, boils at 272, so a -1 Celsius. Acetone boils at about 50-ish Celsius. So it's 50 Celsius higher of a boiling point because of the attraction of these dipoles. So dipole forces are quite strong. We're going to add that to our chart here. So let's get a new color. So we'll say purple is dipole-dipole. Now, the trade-off here is that dipole forces are strong, but only for tiny molecules. So what ends up happening is that we have a strong force, and then we sort of taper off as the molecule gets larger. Now, note that I'm writing relative strength here. So, relative to other intermolecular forces, dispersion is much more significant for a big molecule because there are more electrons. Whereas a dipole occurs between two atoms in a single bond. If I have a dipole and then the rest of my molecule is nonpolar, and the molecule ends up being huge, the polar part is a very tiny part of that molecule. So dipole-dipole is the most significant when there are few atoms present. You'll notice that for all of these examples, we are looking at polarity, but we're looking at molecules that have very small molar masses here. So like less than 70 or 80 or even 100. On the left is propane. Propane is virtually nonpolar. Dimethyl ether is slightly polar. Ethylene oxide is quite polar because it's got that O just all by itself out there making an epoxide. Acetaldehyde and acetonitrile have atoms that are just isolated on one end and make the molecule very, very polar. And so their boiling points go up significantly because they are much more polar. They are more able to stick to other copies of themselves. I didn't realize I hadn't gone to this slide, so there you can see these molecules here. My pen fell on the ground. Let's fix that. There we go. So you can see as dipole moment increases down here, these numbers, the boiling point goes up too. I actually think this is a terrible graph, but I'm not the one that made it. Now, an interesting consequence of this is that things that are polar and things that are nonpolar don't mix together. If you are a molecule that exhibits a permanent dipole, and you have the choice of interacting with either another molecule that exhibits a permanent dipole or a molecule that exhibits a temporary dipole, which choice are you going to make? And the answer is, well, the stronger attraction is always going to form between the two things that permanently exist, right? And so what ends up happening is that anything that has dipole interactions will stick to each other, and anything that only has dispersion sticks to themselves too, but the two things don't mingle together. So this is where the solubility of liquids comes in. Two things will mix together if they are the same polarity, either both polar or both nonpolar. So the term that we use here is like dissolves like. Two things will dissolve in each other if they are both polar or both nonpolar. And we talked about this a little bit in 140. You might remember at the very end when we talked about solutions, we talked about like dissolves like and polar versus nonpolar. This is where that comes from. So now what we're going to do, and I'm going to do these examples for you. You pause the video and do these if you'd like. So we're going to figure out which has the higher boiling point. And this really comes down to which is the most polar. So for instance, I have water and gasoline. Water is polar, and gasoline is nonpolar. Remember that if something is nonpolar, it cannot have dipole-dipole, which means that all it has is dispersion. And dispersion is weak. So something that is nonpolar will always have a lower boiling point than something that is polar, provided that the molecules are relatively the same mass. In this case, it's actually rather close. It's surprisingly close. But water does have the higher boiling point, because water has dipole-dipole interactions. We're going to actually learn that it's a special dipole-dipole interaction in a second here. Here, CH4 is nonpolar. Chloromethane here is polar, and therefore it will have the higher boiling point. Now, HCl and HF are both polar. So we can't just say, oh, which one's the nonpolar one? That's not the answer. However, the electronegativity difference in HCl is lower. So delta En is 3.0 minus 2.1 equals 0.9. But down here, it's 4.0 minus 2.1. So this arrow for this one is much bigger, which means that these are much stronger than these. And therefore, since the polarity is stronger, higher difference in electronegativity, the interactions between those molecules will stick more strongly. So HF should have the higher boiling point. And then finally, between water and ammonia, same thing. Which is more electronegative, N or O? Well, O is, so it's going to have the higher boiling point, because it will have a larger difference in electronegativity. All right. So that's how we predict boiling point with dipole versus dispersion. Dispersion is always going to be the loser if the molecules are relatively the same weight, which I will tell you if they are. I'm not going to say which has a higher boiling point, water or a molecule with molar mass 20,000. Like, that's not fair. There's no way you would know the answer to that. But if I say, oh, okay, water or hexane, assume they're both small molecules. Then you could say, oh, okay, well, hexane is all C's and H's. It's nonpolar. Water is polar. Therefore, water would have the higher boiling point. And that'll work for our examples. Now, the last type of intermolecular force is named really stupidly. I say this as a chemist. No chemist should have called this that. This is what's known as the hydrogen bond. It is not a bond. It is an intermolecular force, so be careful here. A hydrogen bond is just a very powerful dipole-dipole. And it requires two things. Duh, it needs hydrogen. And then it also needs a very, very electronegative atom to be attached to. There are only 3 atoms that qualify for this: nitrogen, oxygen, and fluorine. We're going to have to do Chapter 5 tomorrow during the review. Like, there's just no way around it. Now, what we can do with this orientation is that if I have something very electronegative attached to something very electropositive is the word that I want to use here, I could then point this at another molecule that has the same situation going on. So if I take 2 water molecules and I point them in this orientation, like so, then what I end up having is a very, very strong interaction here. And I can do the same thing with all of these. So here's a strong delta minus and a strong delta plus, because their electronegativity difference between these two is very big. And the same thing exists on this other molecule, so I can form a strong interaction here. So all these dotted lines are my hydrogen bonds. So what you need to make a hydrogen bond is to have your H connected to NO or F, but then you point it and a lone electron pair on another NO or F. And so that's our goal. If you can arrange your molecules such that this occurs, you will form a hydrogen bond, which is the most powerful intermolecular force that we have. So if we go over here, we can add hydrogen bonds to our chart here. Let's get a new color. There, that works. Hydrogen bonds are significantly more strong than dipole. But just like dipole forces, they aren't as effective if the molecule is very, very large. If the molecules are small, these become ridiculously strong, as we're about to see when I show you the boiling point of water on a chart here. Now, let's look at 2 examples here. Ethanol is able to form a hydrogen bond, and the way that this would work is that if this is my molecule, and I'm drawing the molecule very, 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 very loosely here, I could draw a second ethanol, and obviously my geometry is not great here, but that's okay. But I could do that in such a way that my OH points at the electron pair on another ethanol, and these would stick together. Whereas with dimethyl ether here, if I try to draw another one here, I don't have a hydrogen attached to my oxygen, so I can't start the hydrogen bond, nor can I receive one, because the other molecule doesn't have a hydrogen. Oh my god, I'm so sorry. Can't see anything. I'm in a hurry, and that's why I'm like not checking the screen here. Alright. I gotta do it all over again, so I'm wasting time. Alright. Here's one ethanol. I can make a second ethanol. And I can point it at the electron pair on a neighboring ethanol. I kind of missed here, but that's okay. You get the point. So I can form a hydrogen bond here, but because on dimethyl ether there's no attached H, it's not possible for me to form hydrogen bonds between two of these dimethyl ether molecules. So if I was going to compare boiling points of these substances, ethanol should have a much higher boiling point than dimethyl ether. And we can see that that's the case when I give you the data. In fact, it's over 100 is the difference. Dimethyl ether has a boiling point of negative 22 Celsius, but ethanol is 78 Celsius. They have the exact same molar mass, because they're both C2H6O, but all I did was move the O into a place of a C, and then move some H's around for bonding. And that's the only thing that was needed to make the boiling point go up 100 degrees. Sorry, I had to sneeze there. So, hydrogen bonding, really powerful. You'll notice that on this chart, only one molecule can hydrogen bond, and its boiling point is far higher than you would predict from just dispersion or dipole-dipole. So, this line right here, if I draw a sort of dashed line, you can see that boiling point tends to go up with mass, because that's what we're measuring down here. What we would predict to happen is that the same thing should happen for this group of hydrides. So this right here, the blue line is group 14 hydrides, which means that elements in group 14 paired with hydrogen. This is group 16. Group 16 is higher than group 14 because group 16 is more polar. It's further to the right on the periodic table. However, there is an unexplainable jump for water. Water is so much higher in terms of boiling point than anything else in either of these. And the reason for that is because of these very strong dipole-dipole interactions that we just gave a new classification to, hydrogen bonding. Water is the only thing on here that is capable of hydrogen bonds. All right. Of the examples up here, one of these is a liquid at room temperature. Which one is it? I'll give you a few seconds to think about it. Which of these can form the strongest interactions? Well, let's look at them individually. So, formaldehyde is definitely polar. It's got this very polar CO bond. Fluoromethane has a polar CF bond. And hydrogen peroxide is also polar in both of these directions, but because I have an OH, I can form a hydrogen bond. And so if I drew maybe this way, like that, I could then make a hydrogen bond like so. So what you need to be looking out for in drawing these molecules and determining their boiling points relative to each other is, hey, can I hydrogen bond? If so, that's going to be the highest. Hey, is it polar? Okay, that's going to be the next highest. And then dispersion, sort by mass. So these are the forces that cause molecules to stick together to each other. Dispersion, dipole-dipole, and hydrogen bonding. Now, the next force that we have on the next slide is not really an intermolecular force because it's not a molecule that we're working with. It's going to be an ion. But we're going to include it here anyway. Now, you pause the video, of course, to do these examples if you want. We just did HF versus HCl. So we know that HF has a higher boiling point because HF it has a stronger dipole, but HF can also hydrogen bond because fluorine is one of the elements that's eligible, right? Between H2O and H2S, H2O has the higher boiling point because H2O can hydrogen bond. Now, between H2S and H2SE, it's hard to tell because they're very similar in terms of their polarity, but one of them is significantly heavier. So this is the answer that I would give. I would say, I would predict that this one would have the stronger dispersion forces, and that they both have relatively similar polarity because they have very similar electronegativity. S and Se are right next to each other. But Se is significantly bigger. It's twice as big. And then, I'm sure you know what the answer is for this one because ammonia can hydrogen bond. So obviously the answer is ammonium chloride. What? Well, we want higher boiling points. This is covalent, and this is ionic. Right? Ionic compounds use whole charges to hold each other together. Covalent compounds don't. They use intermolecular forces. Ionic will always have a higher boiling point than that. Be careful. You can't forget all of the stuff that we've already learned, right? So, these are the sorts of things that will come up. It'll be like, okay, now I'm going to throw all the topics at you. Which one is the higher boiling point? And if I throw an ionic compound at you, you better not ignore it because ionic compounds have very high boiling points because their bonds are extremely strong. All right, so be careful. This is the last intermolecular force that we really care about. This is called the ion dipole force, and it's responsible for the interactions in dissolving ions into solvents. So this is why water dissolves things like table salt. And so it's not really an intermolecular force because we're not using it to hold molecules together, but instead we're using it to do things like dissociate ionic compounds and hold those ions to other molecules. So even though it's not really an intermolecular force, we could put it on this chart just so you have it all this information handy. So what color will this be? This will be orange. And like, this isn't really going to exist at high molar mass. But the reason that ion dipole is better than an intermolecular force is because the ions are using an entire charge. And so you could think of it this way. What is a stronger interaction? Delta plus and delta minus, or delta plus and just straight up minus? Well, if you look at Coulomb's law, putting in the bigger number makes a bigger charge. So ion dipole forces are stronger than intermolecular forces. Now, because this interaction is powerful enough, it causes things like ionic compounds to dissolve in water. This is why you have to heat sodium chloride to like 1,000 degrees, but it's weak versus water. Because water is very, very polar and capable of forming ion dipole interactions. So there's our summary of intermolecular forces. Dispersion is the weakest force for a very small molecule. It is the strong force for a very large molecule, and is the uneven distribution of electron density. So if I randomly have my electrons scattered around the nucleus or the molecule at large, I can randomly get these interactions. Dipole-dipole interactions are permanent dipoles that attract to other permanent dipoles. Hydrogen bonds are just the strongest dipoles because they have a very large electronegativity difference and they're very, very small. So hydrogen is small, it can get real close to other stuff. And then finally, ion dipoles are kind of a special intermolecular force that occur between actual ions and things like water or solvent. All right. Now, what are intermolecular forces important for? So the things that we're going to talk about very briefly are effects like viscosity, surface tension. So surface tension like water. I'm going to give you these links so that you can watch these on your own. So this is water in space. We're going to just put this here. And so what ends up happening is that this is just a blob of water in a space shuttle, and the blob coalesces into a sphere. You can watch that on your own because I only have 3 minutes to finish this up. Water has a really high surface tension relative to other liquids because its intermolecular forces are very strong. So you can balance stuff on its surface. Like if you put a paperclip on your water and you're very, very careful not to puncture the surface too much, your paperclip will float. So will other light things. So I guess like you could use this for fly fishing or something. But it is cool to see surface tension as a direct consequence of something we've studied. Now, what else can we look at here? We can look at viscosity. Viscosity is how strongly molecules attract to each other when they are forced to move due to a thing like gravity or their own mass or something like that. So if you heat up a liquid and you weaken the forces, the molecules don't attract to each other as much, and then they might spread out more under their own weight or something like that. Now, as you heat up liquids, they become less viscous, right? Viscosity is the ability to resist flow. So something is more viscous if it flows less quickly. So like maple syrup is more viscous than, say, water. Used motor oil is very viscous. Now, if you heat something up, its viscosity goes down. The other thing that you can do is increase intermolecular forces by designing a molecule that has more opportunities for intermolecular forces. Now, the other feature that is important here, because water is not very viscous, obviously, right? Like, water does not look like a sludge. And the reason that water isn't very viscous is that even though the molecules can hook to each other very effectively, they don't get tangled on each other. So they can all flow together. One goes and all the rest of them go after it like lemmings, right? But if you had a molecule like this, where all of the middle part of the molecule is just this big open area for dispersion, and then on the ends you have these pronged carbon hooks where they could all just kind of get stuck on each other like burrs. This would be a prime candidate for something that would have a high viscosity, and this is what's called the pitch drop experiment. Pitch is a very, very viscous compound. In fact, it's so viscous that if you hit it with a hammer, it does shatter. But if you put it in a beaker, it will flow over a long period of time. And this is known as the pitch drop experiment, which is an experiment that's actually going to this day. It was started in 1927. And what they did was they put a sample of pitch in this funnel in a bell jar. And they let it sit there for 3 years. After 3 years, it had filled the funnel and the experiment could start. Can you imagine your lab taking 3 years? And that wasn't even for the first observation. Then they let it run until a drop fell out. And it fell out 8 years later, 1938. And believe it or not, They decided to just let it keep going. This experiment is still going today. I want to say this was done somewhere in Australia. I think it was reproduced in Dublin for the video that I'm going to show you, because nobody has ever captured this drop falling. Nobody ever got to see this until someone had this great idea. You know what? This has been going on for a long time. Why don't we put a webcam in front of it? And so they recorded it. And so this one we will watch because it takes like 20 seconds. All right. So this is the this is Trinity College in Dublin. So this is not the original experiment. This is a different experiment. And you can see, I'm watching a lot of steamed hams, which is why you see the voice of Homer Simpson over there. Steamed hams is such a good Simpsons meme. Do I have this set up right? Okay, so there's our pitch drop right there. Now, in the bottom right corner, you're going to see the timer here. The timer goes real fast. Here's a clock to show you how fast this is going. Wednesday, Thursday, Friday, Saturday, Sunday, Monday, and you can see it's slowly starting to move. Boop, and there it goes. So, like, holy crap. I can't close the window capture. There we go, I'm clicking on the wrong one. Holy crap, that took a long time for it to even start moving, and then all of a sudden it was just like, whoop. So, this is the most viscous stuff ever. And so viscosity is a function of intermolecular forces. I have a little bit, and then I have a link about the pitch drop experiment. So you can read more about the pitch drop experiment if you'd like. I'll paste that in here. And then the last little bit is just capillary action, which is, liquids are attracted to tubes, so they climb up them. Things that aren't attracted to them have convex meniscuses. So water is attracted here, so it goes up like this. So, not attracted to glass, attracted to glass. And the reason that mercury tries to form a sphere in here is because mercury is a metal, and it's all attracted to itself. And you could think of this as like, it just has really, really strong intermolecular forces. Well, mercury is a metal, so it actually has metallic bonding. So it has actual bonds that hold it into a liquid. This is why mercury beads up like crazy if you spill it. Like, it doesn't, like, scatter everywhere. You just get these little beads everywhere. How dense is pitch? I'm not sure, but maybe that Wikipedia article will mention something, so. All right, that is all I have for Chapter 4, thankfully. Hooray, right? So, you can read the summary on your own. We're out of time here. That's all we got. All right, so what I'm going to do is I'm going to put the quiz for Chapter 4 online. Quiz Chapter 4 is going to, it is graded. However, it is going to be open. So when you take the quiz, you will see your results immediately. And you will see your score, but you won't see your score posted on the gradebook. It will show you your score in the quiz, but it will carry over to the gradebook and say, the quiz is awaiting grading. And that's because I had to hit a button. So I'm going to go set that up right now. That will give you some time to work on the quiz over the next few days if you want to use it as a study tool. All the answers will be available, so you'll be able to see those. Tomorrow we're going to do Chapter 5, which will probably take about 30 to 40 to 50 minutes or so, and then the remaining part of the period will be a review. But we will cover all the material. There's no Chapter 5 stuff on the Chapter 4 quiz. But yeah, that's it. I apologize for things going over on time. The tablet thing really threw me for a loop. I thought I was on pace. And yeah, so let me know if you have any questions in the Discord. More than happy to answer them. Otherwise, that was the last lecture, besides the little bit we're going to do tomorrow. So have a good night, and I'll see you tomorrow for the finale. Take care.